There was a time when we thought the world was flat. Of course, we know that isn't true. But let's imagine a world that was flat. I'm not talking about the surface of the earth, but let's try to imagine a world without curved walls, without custom molded furniture, without the Gherkin, the Guggenheim, or the interior of the Alice Tully Hall. It's a pretty deflated thought. But humans by nature are builders. We're always building things. And when we build those things, one very key aspect of that is to build things that work, that are functional, and that are aesthetic. In this program, we show you how to work with resins and push the boundaries to give them shape, form, and function. We're also going to show you how to incorporate these fabrication techniques, inclusive of the element of translucency. It does take a little know-how, but it can make for some amazing applications. Every day, material technology continues to advance. And as the advancements in material technology occur, the methods of fabrication adapt with them. It's just in our nature to go beyond flat, shapeless, formless type structures to be able to achieve not just performance or capabilities, but also to achieve design today. When you consider the fact that resins really do offer an amazing amount of fabrication capabilities, and to be able to do so very inexpensively, now you have a really nice tool as long as you understand the techniques and capabilities of working with those tools. You'll see how working with resins can be very, very simple, very much like traditional materials of fabricating metals and woods. But one thing you will also gain is a knowledge and an understanding of how to work with these materials, incorporating the element of translucency. The key thing about working with resins is you don't have to do anything unusual or different. It can be done very easily with readily available tools. One of the benefits is that on the job site, where you may not actually have perfect construction measurements, you can adapt for that fairly easily with resins by field cutting or field drilling on site. The installation of the product can be something that's very simple, but it can be sometimes complex if you're trying to create these architectural finite details, such as things that are backlit, or even conditions that are really set out just to minimize the visible hardware. The ability to manipulate resin is one of the distinct differentiators that resins have amongst the traditional materials. Measure twice, cut once. It's the #1 rule when getting ready to cut a piece of material. Just the idea of being able to incorporate precision when working with resins is another nice ability to have when developing and designing unique, high design applications. In reality, resins work very much like kind of a translucent plywood. In fact, most resins come in a 4' by 8 format. So when you think about it that way, you have a material that kind of is in the same format as plywood. Wouldn't it be nice if it worked like plywood? Cutting resin with a saw is very easy to do to get those straight, nice finished cuts. Although they do have some unique considerations when you're actually doing the saw cutting. The first consideration would be that of the saw speed. If you feed it too fast, just like wood, you may see splintering. If you feed it too slow, you may actually introduce a little bit of melting of the thermoplastic materials. The only other consideration to make when saw cutting is that of the saw blade type. The best saw blade types are widely available triple-chipped carbide type saw blades. These types of blades are ideal because they give very smooth, uniform cuts and really minimize potential for chipping. Another common cutting method that is often employed with resin is that with a router, sometimes a hand router, or computer numerical control cutting, the CNC machine. This type of cutting lends itself very well to arcs, curves, and things that come to sharp, very high precision tolerances. The main consideration when looking at cutting with a router really involves what type of bit do you use. The best bit designs offer an upcut flute that will allow removal of the debris so as to prevent incidental melting of the material. These bit designs are widely available and very commonly used. A very cool aspect of today's CNC technology is that to be able to work on planes and in three-dimensional surfaces. Later in this program, when we talk about heat forming, you'll actually see the benefits of being able to extend the cutting plane so as to be able to do three-dimensional cuts. This is very easily done with 5-axis CNC router technologies of today. One of the most significant technological advances in fabrication is introduced through that of laser cutting. Laser cutting, like CNC, is very well suited for high precision cutting. The other thing that lasers introduce is the ability to cut multiple pieces very, very quickly. The real big wow of lasers is that the curve size of the laser is so small it allows you to have very sharp inside corners. This is a great technique when you're trying to incorporate very specific geometries within a fabricated panel. Another really nice benefit of working with lasers is the ability to finish edges at the same time while cutting. Oftentimes when using a router or a saw, you'll leave some markings from the saw itself or from the router itself. A laser has a very uniform, solid beam that actually has a nice polishing effect on the material when it's cut, which just makes life easier. Laser cutting does have some limitations. For example, with some thermoplastic materials that tend to be self-extinguishing, you may be limited in the thickness that you'll be able to laser cut the materials at. Materials like polycarbonate and polyesters are very easily laser cut up to about 1/4 of an inch thick. Beyond that, laser cutting is really not a practical technique. Materials such as acrylics, on the other hand, laser cut very easily and smoothly, and they can be processed at thicknesses upwards of 1/2 of an inch. Above thicknesses of 1/2 of an inch, special considerations often need to be made for laser type, laser power, and feed rates of the material that sometimes has to be manipulated through some experimentation. A last consideration when employing laser cutting is that of how is the application going to be used. Though laser cutting can give you really nice finished edges with sharp detail, if you have an application that might experience chemicals such as perfumes, lotions, or things of that nature, you may want to consider a different technique other than laser cutting. You see, when you laser cut an edge, you're actually burning the material away, and that induces a slight amount of heat stress at that edge. Generally, that heat stress at the edge is more susceptible to chemical attack that you wouldn't see in the other cutting techniques. The final cutting technique we'll talk about today is that of water jet cutting. Water jet cutting is actually a very interesting technique, and it's often used when cutting steel or thick gauge metals. Think of water jet cutting as laser cutting, where you're not generating the heat-induced stresses at the edges. So very similar to how laser cutting can give you a very polished edge, water jet cutting actually gives you a nice subtle matte finished edge. A nice benefit of water jet cutting is it's really not thickness limited, nor is it material limited. So you can cut something very simply through high precision at 1/8 inch, for example, but you could also cut something as thick as 3 inches. Water jet cutting tends to be a lot slower. The main difference then is in gaining the ability to be able to give those high precision cuts without edge stress. You are looking at a process that does cost more, but is a classic consideration of employing the right technique in the right situation. Now that we've cut out the pieces, it's time to put the puzzle together. There are several different ways to assemble these pieces to the puzzle. A very common technique is through hardware and mechanical fastening. But mechanical fastening sometimes doesn't achieve the aesthetics that you're after. Two very effective ways to work with resins are through bonding and dry fit joinery. There's two important questions one should ask when arriving at the right bonding technique. The first is what am I going to use to bring these pieces together? The other question is, what are the aesthetics that I'm trying to achieve at this bonded condition? That's really going to determine what the shape of your edge looks like and how you prepare the edges of the parts that are to be bonded together. Once you've answered these two questions, it's time to get started. And when you get started, edge preparation is key. Think of edge preparation as like cooking food. Sometimes the best meals take an hour to prepare, and if they're really good meals, they take 10 minutes to eat. Bonding is not really that much different. Preparation of your edges definitely takes some time to get the best results. Best results in terms of structural stability, best results in terms of aesthetics. Once you've done those things correctly up front and invested the time, the end result can be very satisfying. If you rush the preparation or forget an ingredient, you may have a result that may not be so appetizing because of the translucent nature of the materials. When performing bonding, the choice of glue or adhesive is very critical in determining how to bond certain resins together. The chemical nature of each resin is a little bit different. Acrylic, polycarbonate, polyethylene, polyester. So choosing the correct glue really does make a difference when determining the outcome of a bond in terms of its aesthetics or even its bond integrity. So the right selection of adhesive, solvent, or bonding agent is absolutely critical in achieving a well-bonded part. The other technique that can be employed to put the puzzle pieces together is that through dry fit joinery. Dry fit joinery is a technique that's often employed when your application needs to be dismantled or needs to be able to have some degree of access. Whereas bonding is a very permanent technique, dry fit joinery gives you some flexibility and serviceability to your application. The three loose joinery techniques to employ are half lap, spline, and tongue and groove. These joints are often differentiated in three distinct categories. Those categories would be that of aesthetics, expansion and contraction, and ease of access or movement of the panels. The tongue and groove joint is the one to consider when looking for panel aesthetics. The tongue and groove joint also is a critical technique to give you good alignment from the front surface to the back surface of the panel. It's a great idea to incorporate just a slight reveal. It can be as little as 1/8 of an inch to eliminate any light bleed that may occur from a backlit panel. With a half lap detail, what you're really trying to do is have a detail that allows you to easily access a panel. Unlike a tongue and groove, a half lap is actually completely separated. This could be in situations where there may be mechanical mechanisms behind a panel or perhaps lighting. One thing about a half lap condition is, unlike a tongue and groove, it doesn't have the ability to align the panels with the joint itself. It actually has to be fixed mechanically so that the panels are flush together. Spline joinery is often employed in exterior type applications, where you actually have two separate panels that are being joined together by some media in between the two panels. Joinery that is achieved with a spline condition is mostly being employed to address expansion and contraction issues. The material used to create the spline condition could be resin, but it doesn't have to be. It could be metal, for example. That way it makes for easier assembly of the panels in the field. So with a bonded part, you're very much locking those pieces together. Dry fit joinery is the complete opposite of that, giving you the ability to attach parts, but not make it so permanent. The ability to form and create shape with resin is one of the things that really sets it apart from other materials. It's one thing to have the ability to be formed and shaped, but it's another thing for that ability to be achieved easily. Understanding the notion of easily can actually mean several different things. One is that it can be achieved with very simple equipment. The other notion is that it can be done efficiently at a very low cost, whether it be in high volume or actually just low utilization of energy. You see, thermoplastic materials, in their very nature, have forming temperatures and softening temperatures that are way less than that of other materials. Think of when you form glass. Forming glass, you're looking at temperatures well in excess of 1,000 degrees. But with resins, most resins can be formed under 350 degrees. That's a big difference. One of the easiest methods to create form and shape with a resin is that just through simple cold bending. With simple cold bending, the materials are very ductile, but they're also very flexible, and you can do pretty amazing detailed bends with the resin. Sometimes you can even do, ruled surface type bends in a lot of different directions. The ability to cold bend resin really does create a nice performance, aesthetic, and even cost benefit in certain applications. One thing to consider when thinking about cold bending a material, though, would be first, the minimum cold bend radius. Generally speaking, the cold bend radius for any resin material, thermoplastic material, is about 100 times the thickness of the material. So for example, take a material that's 1/4 of an inch thick. Your minimum bend radius for that material would be about 25 inches. There are some complexities that are involved when considering cold bending, but material consultants and fabricators understand this very well and can help guide you in your designs. Another thing to consider when cold bending is the hardware required to achieve the bend. A lot of times cold bending is best done in a framing condition or with cable and rod type systems. This allows you to change direction with the panel and still achieve a really interesting look without having to incorporate heat forming. More often than not, this technique is best employed with thinner materials that have thicknesses less than 1/8 of an inch. Complex heat forming is one of the main separators of resins from other materials. Just the very notion of them being thermoplastic, heat formable materials really does allow you to do some amazing things with resins. Think about complex shapes, curves, designs that incorporate twisting and turning and undulations. It's a collision of art and architecture. So to incorporate a more permanent shape, heat forming techniques need to be employed. The first, and probably most simple, is that of simple line bending. With line bending, typically a section of the material is heated up just above its softening temperature. And then the material is easily worked to conform to a radius or even at a slight angle to create some structure and shape in the material. Line bending is a great technique to incorporate structure into a panel with minimal use of hardware. For example, by taking a long piece, you can actually get a nice long span and keep a very straight and rigid material. This is pretty effective with resins because they tend to have a higher degree of flexibility, which is why they're so impact resistant. Line bending can really do a great job in terms of incorporating some structure with eliminating the need for bonding or seaming, or putting in additional mechanical hardware to create structure. So you're trying to create shape in your design, and simple cold bending is not really going to cut it. Nor is line bending. You really want to kick it up a notch. That's when you incorporate complex geometries into your design. So not only does incorporating this third dimension of shape really have an aesthetic benefit, just like in line bending, it incorporates additional structural integrity into the materials that really allows it to be used in a myriad of applications. A really nice thing to incorporate with your design is the ability to rationalize that geometry to use a single mold for multiple shapes, therefore decreasing the cost. Designs with rationalized shapes can become a tool in your palette, so some impressive designs can be achieved with just a single basic shape. The other thing that rationalizing the geometry does is it maximizes the material yield, so little or no waste is generated in creating the three-dimensional part. Because of geometry rationalization, shapes can actually be used in a lot of different applications. So in a lot of cases, if you needed a design that was ready to go, you could consider as few as one or even two shapes to create an impressive design.
Over the past 6 years, 3Form has pioneered fabrication techniques for our resin material. We have developed many processes that have allowed us to manipulate resin through the machinery and through the talent we have hired to make this possible. Threeform has created a world-class training program that has been able to develop people from all different trades, whether it be architectural millwork, glass, plastics, and the metal industry, into the most skilled resin fabricators in the world. Threeform has amazing engineering capabilities. Using our customers' drawings, we create and engineer fabrication drawings for each of the Threeform sheets that we manufacture and fabricate. Once the engineering is complete, then the drawings and the cut lists go out to the factory in order to start producing our customers' projects. Cutting resins is a very technical process. One of the first steps in machining resin is to cut the flat sheets per our customer specifications. We do this with either a panel saw or a CNC router. Our panel saw combines a misting system with carbide saw blades that allows the resin to stay cool while cutting them cleanly without creating stress in the material. Another method is to cut the sheets using a CNC router. CNC means computerized numerical control. This router translates programs such as AutoCAD, Rhino, or SolidWorks to achieve very precise geometry. There are basically two types of CNCs. The first is called a 3-axis CNC. The 3-axis CNC is a high production router that allows us to machine the resin very quickly. 3-axis means the ability to cut 3 linear axes. The 5-axis CNC is capable of routing complex geometries. What this means is a 5-axis CNC not only cuts in the X, Y, and Z axis. With a 5-axis CNC, the head also tilts and rotates to allow the cutting of even the most unique design geometries. Given this technology, if you can imagine it, we can achieve it. Once the machining is complete, the material then goes to one of our many highly skilled fabricators who will seam and fabricate your projects to your specifications. We try to stay very current on breakthroughs in adhesives and different types of joinery which allow us to be more successful in our seaming processes. In translucent material, air is our enemy. When introducing glue to a translucent material, it is crucial to be able to get full glue coverage. Otherwise, you have a greater risk of getting air in the seam. One of the most amazing characteristics of resins is the ability to heat form the material. Threeform has 2 very large ovens that allow us to heat form from very small parts up to parts 20 feet in length. We heat form resin materials anywhere from 1/4 of an inch thick up to 2 inches thick. We use custom-built molds for every job per our customer specifications for radiuses and dimensions. The 3Form material has the ability to be cut and shaped much like wood does. We use many types of machinery such as shapers. Shapers use carbide tooling to machine many types of edge conditions such as tongue and groove, half lap, or mitered joinery conditions. Threeform has the ability of painting custom millwork projects as well as clear coating our resin materials. Threeform also has custom powder coating technology, which allow us to custom powder coat any of our 3Form hardware solutions as well as custom hardware solutions. It has taken years for 3Form to develop the skills, techniques, and processes that now lead the industry in fabricating translucent material.